So in this recording, I'm going to take you through a sort of really super fast introduction to how you can set up Ghidra on your computer. So Ghidra is this nice reverse engineering tool for disassembling binaries and has a decompiler so we can see C basically out of it. So it generates C code from the binary that it disassembles, which is sort of a nicer way sometimes to look at the structure of these codes. So if you download Ghidra, what it's going to give you is this zip file. And there's a little installation guide here that's going to go over what you need to do. So it'll work on Windows, Linux, or Mac. Now, if you're on Windows, I have an easier solution for you, which on this GitHub for the ECED4406, there's a releases thing, and I just use this to give you the zip file. So if you go to this releases, what you'll see is there's a zip file you can download here. And this has built in the Java runtime environment. So you might not have Java runtime environment installed. You might not want to install it system-wide on your computer. I try to avoid that, to be honest. So this, I've just packaged the two together and put it up here. So there's no other real changes. I don't know why this says 1.8.2. Ignore that. That's going to be fixed. It's 9.1.2. So it'll download. It'll take a second. And all you'll have to do is whatever your zip extractor tool is, right? We'll just open it. So probably you have Windows. I have 7-zip set up here. Probably you have the Windows zip thing. So you need to extract it somewhere. You don't want to just open it. So you could either copy this somewhere. So for example, I could copy this even to my desktop. Doesn't really matter where. Possibly there shouldn't be spaces. If there's spaces in your username, that might cause trouble. I can't remember now. So apparently this is gonna be slow. Yeah, so once that downloads, what we're gonna do, so if you're not on Windows, you'll have to follow some of the installation guides, and there's some videos of this you can find online too. But you basically just have to install a JRE is the issue, so, okay. And this, what I'm following here is this Ghidra Setup intro, by the way. So there's a slide deck that is going to go through all the stuff I'm going to do. So, you know, if you want any of this written down, it's available here. So don't worry if it's going a little fast. You can follow along with this slide deck. So, okay. Oh. Something's going wrong here. Oh, right, okay, I already had it there, so I'm kind of cheating. Should have just skipped it, but we'll copy everything over and keep running. Okay. So in the meantime, what I'm going to explain, well, that's unzipping. We need something that we're going to disassemble, right? So we need some example code. What I've dumped into this folder, so I've tried to kind of put everything you might need in this one folder. There's a code from the Chip Whisperer examples, so that you don't really care what it is. I just needed something that was some Cortex-M code that you can look at. So this is Chip Whisperer has some applications that we can compile. One of them is this basic password check. So this is like a little password check. So you can look at the code here and you can see what it does, right? It prints some stuff. It asks for a password and then it compares the password, right? So this is the C code that you would see or the designer would see. We've taken that, we've compiled that to a binary. And in this same folder, what I've shoved is two binary-ish files. So there's an ELF file and a hex file. And we're going to use a .hex instead of a .bin because it won't require us to know the base address. So one of the first things you'll have to do is figure out the base address. So we're going to kind of skip that and use this hex file. It's very, you're not saving much by doing that, but it's a little easier to get started, I think. There's also an ELF file I included, so we can open that after and see what it has in it if we load it. So you wouldn't normally have a .elf file, so that's pretty unrealistic. The .hex, though, is pretty realistic. This is like if you read it out of a chip or anything like that. So that's kind of what you would get as a reverse engineer. You would just get that hex file. We also know this file was an STM32F303, so what I've done is I've gone ahead and copied the datasheet right in here for you. So you have the full, this is actually the full reference manual, not the data sheet. So this has all sorts of stuff, so you'll probably want to open it in a real PDF viewer. Of importance, it has the address of where certain things are. So okay, let's see if my unzip is done yet. I think this is stuck again somewhere. Where did you get stuck? There we go. So we're good. So now what we have, if I move this window, I have Ghidra. So compared to if you just downloaded the zip file, the difference here is that we have like a JD key, the Java development kit, Java runtime engine and stuff. So these folders have been copied in for you, and basically there's some changes to this Ghidra run. All I've done is it adds a link to, so this is the magic, it adds a link to the Java runtime that's in this folder. So that's the only difference from one that I downloaded, is adding this line and adding these two folders. So it should just work though if you hit Ghidra run.bat. So again, on Windows, what you should get is, in this case I've already run Ghidra, so it should pop up a, so let me just close all this stuff. It should pop up a, you want to accept this agreement thing first, and you'll have something that looks like this. It'll say no active project. So what we have to do is, the first thing we're going to do is we're going to make a project. So we'll go File, New Project. We can either have shared projects, which if you're working with multiple people is handy, or non-shared project. I'll leave it as non-shared for now, and we'll just put it somewhere. So we need a project directory. This should be like your documents folder or something. So I'm going to make a new folder here. New folder, we're going to call it temp2, and we're going to give it a project name, ECED4406 intro. Looking good. Okay, so this is it. So we get this blank canvas here. Now what we need to do is we need to import a file, so file import, and this is pointing to basically if you download that .hex file, right? So if I go here and I go hex, right? It's displaying it. It's trying to display it in text. We actually want to hit, if you hit raw, it's going to show it in your browser probably. So what you want to do is if you right click on the raw button, let's move that so you can see it, and hit save link as, it'll let you save this wherever you are. So right, this is saving it to this, but we could save that to our desktop and hit save. Okay. So then when I go file import, right, I could go to my desktop and get that. Okay, so the important thing here is it's saying this is the file we're going to import. It says please select language, right? So language means, and it auto-detected, by the way, the format, so Intel hex, that's good. It only has a few options here, right, but that's what we want. So language is basically the processor type, right? So you can see a whole bunch of stuff. What we have is a Cortex-M, and so if I went back to my, where's this, 4406, here's that device data sheet, right? And it tells you right here, ARM Cortex M4 with floating point unit. So it's an ARM Cortex M4. Ghidra by default doesn't have much more than Cortex. So there's sort of, so what you can do here is you type Cortex to see all of them. There's going to be a really nice thing that we're going to do after is setting up what's called SVD files. So these will map a whole bunch of peripherals and stuff for us. So this is a really handy way to work with little embedded devices. But for now, let's not worry about that. Let's just do a base Cortex addition. So I'll say language processor is ARM Cortex. Little endian is very important. Technically, some of the devices I think can have either. Little endian is more common, so you can just use that by default for Cortex devices. Cortex M, sorry, that is. And hit OK. So there's some options that we might have to specify. So there's some other stuff we'd have to specify if it wasn't a hex file. We don't have to worry about that. Let's just hit OK. You'll get a little summary thing that says what it did or is doing or whatever. And there we go. So nothing too important with that. Wait for that to happen. Let's move this stuff out of the way a bit. Okay, so that happened. That imported. It doesn't look like anything. What you need to do is we want to open this. So if we double click on this, it's going to open it in this code browser tool. The first thing it's going to ask you is, do you want to analyze it now? So we normally will just hit yes here. So this is going to look through, because it's just opened the binary file. It needs to figure out what are instructions, because some of this is data storage and stuff like that. So let's analyze it, right? I'm going to leave these all as default. So there's different stuff that it's looking for. You can see it's looking for like ASCII strings, right? So it sort of looks for a string. There's some minimum string length, right? And it's going to look for like the null characters at the end and stuff like that. So it has ways that it's trying to find what these strings are, because those might be referenced by the code and things like that. So some of these you can actually change settings. Some of them you can't, right? So like it's looking for ARM symbols, analyze bytes for thumb symbols, right? So this is like if you're in ARM versus thumb mode, there's a address offset of just a single number, because if it's in thumb mode, you're using like the lowest bit is set to 1. So basically will end in a 1 instead of a 0 or 2. So it just does some necessary changes like that. So we're just going to let it all be default and hit analyze. And you'll see at the bottom, it was really fast here, but right here, there was a little status saying what was going on. Let's make myself smaller. There we go. You don't really need me here. So this is what it looks like now. So if you just scroll down kind of, right, you can see a bunch of disassembly code on the left here. And if you click somewhere, it's automatically giving you the decompiled view of it, right? So right away, we can see that it's taking the assembly code and converting it to C. When it does this, though, of course, it doesn't know anything about, like, so this function A, and this is in general, right? So this applies to the disassembly. Everything's called, like, whatever the address is. So this 800 something is an address. It doesn't know what this function does. It doesn't know the name of it. It doesn't know the name of the parameters. It doesn't know name of local variables. So this is part of the reverse engineering, is that this is what you would typically be kind of given, is code where you don't necessarily know a whole lot about what's going on. And what you can do is you can look for constants, you can look for strings, you can look for a lot of stuff that gives you hints about what the different code is doing. So this is the kind of the, puzzle-like aspect of reverse engineering, is figuring out how all these blocks fit together. So a few things that we can use is, if we go back here, okay, close this, right? So as part of the setup, I tell you to go through a few different examples, or as part of the lecture, actually, I went through a few different examples. So one thing you could do, for example, is you could look at strings. So if you said tool window define strings, right? all of a sudden we see some strings in here, right? If this was something that we didn't know, this was maybe a device we can run and we can see these strings printed out the serial port. That's pretty interesting because it's like, here's an access granted, here's a password fail, right? So if we look at where this is used, let's just double click on that, right? It's going to the string. So a big part of Ghidra is this cross-reference thing. So if we look at password fail, right, we can see these cross-references to some different locations. So if we look at this function call here, let's just click on that, right? We see a reference to the password fail, which is probably, like, that sounds like some pretty interesting stuff going on around there. And now let's click back to our decompiler. We can see, like, this, if I had used this device, I would know that, hey, it actually prints these strings when it's booting. So this is a pretty good indicator that, let's make me fit right in there. Perfect. This is a pretty good indicator. This might be like the main function, right? So because we can sort of read this and say, okay, well, here's our strings. Please enter password to continue. Password fail is here. Access granted is here, right? So now I have a pretty good idea. Well, somewhere in here, it's going to be reading from the serial port and doing the password comparison. So we might be able to figure out where the password's stored. So we might be able to actually figure out what the password is by analyzing this code and looking at wherever it's storing that password. If you didn't know, so the other thing is we could try to figure out, right, like, what's this function? Well, this function gets called with a pointer to a string. That seems like it's probably like some sort of string, like print or something like that. And if I know that's printed over the serial port, that's pretty obvious. So in the lecture, the Intro to Ghidra lecture, or Finding Functions lecture, actually as part of the 4406, I sort of went through an example of this, right, we could look at this function. We could see there's a loop, and the loop is taking in this param1. The nice thing you can do is if I'm like, okay, well, this loop takes in this pointer to an array and then goes through the array until it's not equal to 0. This is probably a string. So let's rename that to like input string or whatever we want to call it, right? To make this a little more obvious. So it's like, okay, here it's incrementing the string until it's reach the null termination of the string, and then it calls this other function, right? So let's look at this other function. And the other thing we can do is we can name these functions, right? So if I'm looking at this code, I might want to rename this function. I don't know exactly what it does yet, but I could say like, print string to serial port. Right? We can give it really complicated names if we want that describe what it does. Like this might be just a puts or something, but I don't actually know if it's the low-level function, it's the high-level function or something like that. If I go back, so up here there's a back button, and this goes to the previous location. We can now see that it's renamed these functions everywhere they're used. So it's a lot easier to see them when they're in use. There's some other function call we don't know what it is yet. But you can see this guy here is somehow printing a string to the serial port, I think. And I think that because I saw those strings come across the serial port. So inside this, it's calling this other function, which is called with a single character. This is probably like a put character function, I would guess, right? But how could we confirm that? One thing you'll notice right away is that this is claiming there's a single input character, then all of a sudden it looks like there's more stuff going on here. So it doesn't always guess correctly how many parameters are being used in the function call. So that's something that you should be aware of here. But what we see is another call to some unknown function. If we look at that function looks a lot crazier. So let's go back for now and let's look at the arguments, right? There's one argument here that's a little unknown. If we look at this, so this is just pointing this dat 800 whatever, right? Is if we either hover on that, it'll pop up, or if I double click, it goes to it over here. What you can see is this is basically just a constant. So it looks like it's some, this is normally what happens when you have like global variables. So this looks like a pointer to this address here, right? So I might want to rename that to make it more obvious for now. So if I hit rename global, right, I could call it pointer to 2, 1, 2, 3, 4, 5, 9, 4. All right, so now the issue is, what is this? So this is somewhere in RAM. And how do I know that? I know that because if I look back at, where's this? This reference manual. So somewhere in this reference manual, there's going to be a memory map. And this is really important. Let's see if we can find it quickly. Let's just go ahead and download. I'm going to open this in a real viewer. So now we have this in Adobe, so we can actually search it and stuff like that. So here's the memory map for the device, right? So if I go down to down here, we see this address. So from whatever this address is, this is in SRAM, right? So this is where all your variables and stuff are going to be stored. So what we actually would like to do is, if we told Ghidra that this was SRAM, this is going to actually improve our analysis. So we should have done that initially, but let's do that now. And that's something we'll look at after with the SVD file. So I'm going to go up to Window. Where's the memory manager? Oh, memory map, right? Okay, window memory map. So this is just guessing that it has RAM here. Technically, it's flash, but it doesn't really matter. So it can execute from this memory. Technically, I guess it can't write to it easily. So we could say you can't write. So that's ones that are just guessed based on where it saw code. So let's add a new code source. Let's say it's RAM. It starts at that address. What length is it? Well, if we go back to our reference manual, we saw it was it ends at 9FFF. It's 40K, so I'm just going to say the length is that, because it'll add these two together. So we'll go start from here to here, and that should give us the total SRAM size, and we can give it the block name of SRAM. Right, and we can write there, we can read there. I think you can actually execute from it. So let's just do that. So now we have SRAM at that location. So if I close the memory map, what changed? Well, now if I click on this, so what changed is that if I go here, I can go to that address, and it's actually pointing to a new variable. So there's some variable, it has no idea what it is. It's called this memory address, basically, because it's at this memory address, we have some data. So if we knew what type of data it was, we can actually tell Ghidra, that this is a word or something like that, or whatever it is, if we saw what size of data was being accessed, right? So if you actually knew the type of data, you can improve it a little bit by confirming, right? If it was just a byte or whatever it is, an int, right? So in this case, whatever this is. We don't really care too much right now. What we're going to look at is these cross-references. So everything in Ghidra, you're basically just doing all these cross-references between stuff. And we can see that this variable here, let's change this back to Word. Okay. This cross-reference here is being loaded with something. So that's actually being loaded, and this is where it gets confusing, right? As you can see, like it basically is loading another reference here. So it gets a little easier. So why you kind of like the disassembler is that if we get these, so you can see the combination, right? So if we look at this, we can sort of see that the word here, right, is getting loaded with this constant value. So from the disassembly on the left here, that might be a bit confusing, but the decompiler has made your life a little bit easier because you can see this word is actually just getting loaded with this one constant. And if we look at that word, right, it's not getting overwritten anywhere else. There's only one point in the entire code base that it gets loaded. So this seems like it's a global variable that's set once, that's initialized, and then not overwritten. So we could really say that this word here is actually just getting loaded with this value. So, you know, we could rename this, edit label. So what I hit, I think it went off screen for you. If I go down all the way here, there's a label, add label thing. So we could just call it, like for now, right, we could call it fixed or const, whatever, right? Because that seems to be what the value's loaded at. So I'm taking a bit of a guess here. Now if we go back, so remember the whole point of this, right, was that we had this, go way back. Where was that? Are we there yet? Okay. Here we are. So in this code here, or not this code, sorry, let's go back to this code. In this code here, we had a reference to that random address. Well, now we can see that random address, we've given it a label. So now Ghidra says, oh, okay, that's okay. That address is just this constant value. What's that value? Why is that interesting? Well, in our memory map, you'll notice that the 4000 series for this STM device is all the peripherals. So this is actually dealing with some sort of peripheral. So if we go look for 4001. So on this page, 3800, oh, that's actually USR1. So we could then rename this, rename global USR1, because it looks like it's just pointing at the USR1. So now this makes a lot of sense, right? Now what we can see is we have a function that's being passed a pointer to the UART, so the serial port hardware. This function is called from somewhere that's printing to the serial port. So this seems like this function is like print to USR1 somehow, right? So print char to USR1. So I don't know exactly what the other stuff is. You know, maybe there's some timeout or whatever. But I could figure out by going through these what some of this stuff is. And now anywhere I see these reference, right? So now in this print string, it's pretty clear, like, it gets a byte and then sends it out to USR1. But if you get this up, so the point of this video is to kind of show you, how to open a new file in Ghidra and how to start playing around a little bit with it. So there's a lot more that you can do. The one nice thing, so you saw with this, I had to do a lot of work going back and forth between the datasheet and all this stuff. What we're going to look at is also how you can figure out, so if I open up that, where does this go? Right, if I go back here, there's this other file type that was included, this SVD file. This actually has a bunch of the stuff encoded in it. So there's ways to get these files that actually know at what address USR1 is, and we can connect that to Ghidra. So someone who is much better at Ghidra than me, Thomas Roth, has made this really nice tool for basically doing that and helping you understand so rather than having to go through and manually add like all of these peripherals and the SRAM sections, it's just there. So it would be really obvious when you look at the code that you're using USART1. But before you deal with that, let's just get Ghidra up and start exploring a few binaries to get a feel for it.